All right, welcome everyone. I am JJ. Let's go ahead and tackle an example problem. So we're just saying on this one, let's find our support reactions. We have some objects shown. There's a trapezoidal distributed load on it, two concentrated forces, and a couple moment here. Then supported by a pin at A and cable BC. We want to figure out what is going on in A and BC. So AX, AY, and our tension. Three unknowns for us to get through. So our first step in here, anytime I'm applying equilibrium equations, we should make a free body diagram that goes with it. So let's tackle our free body diagram of our object here. So we should be able to draw, we have from A to B all the way down to the bottom is one piece in here. So we can come in and draw that in. I know at A, I have a pin, so I'll get in an AY, I'm going to guess it goes up, and an AX, which I'll guess goes to the left. Two unknowns there. I have my trapezoidal distributed load on here. It starts 2 feet in, 2 feet, yeah, 2 feet in, and goes for the next 12 feet. We'll say that ends about right here. And then there's 6 feet to get out to the right edge of this. Going down, we drop down 8 feet. So I can get that labeled as well. Let's get that distributed load in here. On the left edge, our short edge, we are at a height of, 10 kips per foot? 10, so label that. And on the right edge, we are up at 15 kips per foot. So 15 out here, kips per foot as we go in there. At my corner right here, I have my cable. I know cables always have one force in tension, so I can come in right here and put in a tension and cable BC, or just TB, that's what I'm going to call it. And given that is a 30-degree angle. So we know the angle as well. At the bottom of this, 8 feet down, I have going straight down a 12 kip force. Straight down, 12. I have to the left, 25 kips, 25. And there's an applied couple moment here. It is going counterclockwise, and we're given it is 200 kip feet. So 200 kip feet. Our distributed loads in kips per foot for both of these. Kips per foot. TB 12 kips, 25 kips. We can come in and apply equilibrium to that. We have our free body diagram set up. Let's make our equations. So what do we want to do first? Well, I would count them off. If I sum forces in the x first, I'd have AX and TB, two unknowns. If I sum forces in the y, I'd have AY and TB, two unknowns. Ideally, there's somewhere then that I can sum moments about and get rid of two of my unknowns. And realistically, I could do that here at B. I'd eliminate TB and AX. Or I could do this at A, I'd eliminate AX and AY. Either way, I'm getting down to just one unknown. I think the more obvious choice is A, because it's really easy to see AX and AY there. So let's do moments a day. So moments with counterclockwise being positive. Positive goes counterclockwise. Let's sum up all our moments about point A. This should get us in here. Well, we have our applied couple moment on that, 200 kip feet. So 200. Our tension's y component will cause a counterclockwise rotation about A. So plus TB times the sine of 30. Again, that gets us our y component. Times our distance in here, 2 plus 12 plus 6 is 20. So times 20. Our 12 kip force, that's going to cause a clockwise rotation. I took counterclockwise was positive, so minus 12, our force, times our distance, 2 plus 12 plus 6 is 20. And I think I can get one more piece in here. The 25 will cause a clockwise rotation, so minus, the force is 25. That's an x force, so I need a y distance back to A, 8 feet times 8. And we'll just wrap that on the next line. I still have to get my distributed load in here. So if I have a trapezoid, I need to break that into a rectangle with a triangle stuck on top of it. We're really kind of breaking it right here. That triangle is the difference between the tall side and the short side. The rectangle's height is just the short side. So my rectangle has a height of 10 kips per foot. Let's deal with that first. It will cause a clockwise rotation, so minus the force for a distributed load is the area of it, so minus the area. That'd be 10 times 12. If I have force, I'm looking for moment though, I need to multiply by distance one more time. So my distance for a rectangle, I need to get to the dead center of the distributed load. So from A to get to the center, I'd have to say, well, first I need to go in 2 feet to get to the beginning of the distributed load. From the beginning, I go half the width. So 2 plus 12 over 2, 2 plus 6, my distance here is 8. And then I can come in and say, what about the triangle portion? It's also clockwise, so minus, I need area times distance to get force times distance again. So my area here is 1/2, my base is 12, my height is 15 minus 10, 15 minus 10, that tall side minus the small side, because the first 10 already went to our rectangle here. We only want the 5 that's the triangle. Times our distance, which the distance for a triangular distributed load measures 1/3 of the way in from our 90-degree corner, or from the far right edge on this. So I need to get from A to the right edge, and then we can apply that 1/3 of the way in rule. So to get to that right edge, I go 2 plus 12, 2 plus 12, and then coming back towards A to come 1/3 of the way in, so I'm subtracting off 1/3 of my distance, minus 12/3. Or this is really 2 plus 12 is 14, minus 14, or minus 12/3 minus 4. I get 10 is my distance here. But all of that's going to add up and get me to 0, which I have TB is my only unknown in here. I can solve for TB. I'm going to get that the tension in cable B is 150 kips. And we are in tension. From there, I can go and say with TB known, I have 2 unknowns left. I can sum forces and get both of those. So let's just sum forces in our x direction. Summing forces in the x. I have the x component of TB. So TB I know is 150. I'm looking for the x component. So cosine of 30. I have 25 goes to the left, minus 25. And we guess that AX goes to the left. So we're going to subtract it out, minus AX. And that's going to get us to 0. Or solving for AX, we just get the AX is 104.9 kips. I get a positive number coming out for this one right here, which means I guess the correct direction up above. Let's stick that direction in our final answer here. It is to the left. And then finally, I need AY. Let's just sum forces in the Y, and we'll get there. Summing up my forces in the Y direction. I have AY going up. I have TB goes up, so plus TB is 150. To get the Y component, I need the sine of 30. I have 12 coming down, so minus 12. I have my triangle or my rectangular distributed load. If I'm just looking for the force here, summing forces, I just want the area. It's pointing downward, so minus base times height, 12 times 10. And then finally, I need to subtract off the triangle's area as well. So minus 1/2. My base is 12. My height is, again, the difference in between the two sides, 15 minus 10. And that should, do I have everything? 1, 2, 3, 4, 5. That should be everything. Equals 0. AY is our only unknown. If we solve for AY, we're going to get here that AY is 87 kips. And it is going straight up, which will be our final answer for our problem. Hopefully this is a useful video for us, just showing how do we deal. Specifically, the challenging part is that trapezoidal distributed loads. But we can get through these. You can do this. If this was useful, hit those like and subscribe buttons. Stick around, watch more videos. Let's get you an A with JJ.